Okay, so for the past few years, I've been experimenting with drone photography, and by using different filters, I've been able to image in the near infrared and near ultraviolet. And in the course of this, I've been also experimenting with nighttime photography using the drone, in particular, using the drone for use in astrophotography. So astrophotography is by having a camera set up at night and taking long exposure photographs of the night sky. It's a way in which we can see deeper into the night sky, and also to see some night sky objects, deep sky objects that would otherwise be invisible. And we don't have to necessarily use a telescope to do this. We can actually use a fairly large camera, such as the Hasselblad camera on the DJI Mavic Pro 2. And using this camera, which is a 20 megapixel camera, I've been able to create nighttime astrophotography photos. And the added advantage is that I had modified the camera to be able to see in the near infrared and near ultraviolet, essentially to make it into a multispectral camera. But by having no filter, I was able to get a full view of the night sky with no blocking or no interference caused by optics. So that being said, I was able to, over the course of a few nights, take some photographs by flying the drone and also having the drone stable on the ground, but mostly by having the drone fly a couple of 100 meters into the sky. And from this, I was able to take some very interesting photographs, both DNG, the raw format of the drone photography, and also in JPEG. So the DNG or raw files have to be processed and have to be output as JPEGs for them to be used in other commercial software. However, I was also interested in developing my own exposure enhancing software in Python, and using Python I was able to create 4 different codes, actually 5. One was the general one, 4 different codes that are able to do different exposure stacking procedures. So I have here one of the codes. These have to be used in the directory with the files that use the DNG files as inputs. They have to be processed using a section of the code. The first section of the code has to process the DNG files and then output them as JPEG images. And then the second part of the code searches the directory for the output JPEG images, and then uses the exposure stacking procedure using the Python FN match library. So that has to be pip installed first, and also using exposure from Sky Image and other directories as well. The raw Pi library also is able to process the DNG images in the first place. So to use this code, you have to first install do like a pip install of, say for example, FN match, and then you should be able to use it. However, the main point is that I was able to process the files, but I first had to take the files first, and some of the outputs you see here are of many different images. I think 46 images stacked on top of each other, and using a exposure stacking. One of the codes, I can't remember which one for this case, I think it may have been the averaging, and I was able to take a series of photographs really, of different sections of the night sky. So you see this is the photograph here, one of the original ones, and you can see as I move along, you can't really make out that much, but once you process them, you can make out some of the deep sky objects. So this, if I zoom in, I can see the constellation here, Cassiopeia. You can see the kind of crown shape, W shape. Sometimes common constellation you can see in the night sky, and this then points directly to this kind of kind of witch's hat shaped, pointy, kind of horn shaped image, which is Andromeda, the constellation Andromeda. So in between these two constellations, Cassiopeia and Andromeda, we have, of course, the Andromeda Galaxy. So the Andromeda Galaxy is a deep sky object. I mean, in textbooks, you'll see it's visible to the naked eye barely, but in most areas, it is very hard to see, if not impossible. Even through a pair of binoculars, it's basically just a smear or kind of a smudgy star. Doesn't look like very much, but here it's clearly visible because of the exposure stacking. You can make out the kind of disk, kind of nebula appearance of it, but this is actually the Andromeda Galaxy. So very interesting to be able to see this through the drone using a exposure stacking procedure. So this technology is obviously very interesting, very useful. So I will do a demonstration of it being used. So I was able to take these photographs over the course of a few nights, testing them in different locations, as I said, from the ground and also from the sky. The best photos I took were from the sky at an altitude of about 300 meters. I was able to fly the drone and take these images. So these are the images I took on day or night 4 rather, and I was able to process them. And I processed the DNG files first, and I will show you how the code works. So I can use any one of these 4 codes. Incidentally, these are all available on my GitHub page, so if you want to download them, they're free for use. They're on this section here, Mu1Ray, Python, DNG, drone astrophotography. You can use, download, modify, you can do anything you want with these codes. These are all public domain, Creative Commons, whatever you like. They all have the details of what the code does, and you can toy it around yourself and experiment. They're experimental codes, they're not perfect. I will also show you a really good commercial, or I should say freeware, not commercial, it's actually for free, software called Sequator, which is here. I will show you this in a moment. Sequator is a really good freeware for processing photos for astrophotography, for stacking them, doing exposure stacking and improving the signal to noise ratio of the images. But first I'll show you the code working. So the DNG processing, we can use brightness processing, averaging processing, exposure, clipping pixel processing, or scaling summing processing. I think I'll use the scaling summing processing, and I will run the code. It has to be run in the directory, and as it runs, it actually outputs the JPEG images output. So it takes a while for it to process, but as it's running here, I can show you as it inputs the DNG files, the raw files, it then outputs the JPEG files, and they look a bit strange. They were taken, remember, in basically mostly near infrared. That's actually the dominant wavelength that the silicon sensor in the Hasselblad is sensitive to. Which you can see here, after a few minutes, it should begin to output the JPEG files processed. So for DJI 500 here, it should then output a DJI 500 JPEG, and it should do this for all of the images as it runs in the background here. So yeah, it's going to output DJI 500 here. It's going to create the file and then fill it up with the code of things running in the background. So if you've anything running in the background, it may take some time for this code to work through. The DNG files are quite large. Each one is about 30 or so megabytes, or 33 megabytes in this case. So you can see the output is much smaller because it's a JPEG image, and obviously some of the information has been lost in the processing, but that's okay because it enhances the gamma correction. It does histogram equalization, gamma correction, and so on in this code. So you can see here, you can already make out some of the stars, Cassiopeia here, a little bit of Andromeda, but we can't make out quite yet the Andromeda Galaxy. It's kind of a little bit of a smudge here, but we can't make it out. To make it out, we need to we need to stack all of these images together. And this is what the code does. It will output a brightness image that will be more similar to this image here, with some, as I said, gamma correction, histogram equalization, and so on for the color. And as that's working, it will output each of the images. So I'll just have to let it run its course for a few minutes. Again, as I said, it takes a while. It has to process all of these images, 46 images, I believe, and we will then be able to see the code run at the end, and it will then stack all of the images together, the JPEG images, by reading them in the directory, and it will then output the exposure stacked image using the scaling summing in this case. And we can also then use, when this is finished, I will show you, we can use each of these individual output JPEGs in the Sequator. We can also use it in the Sequator freeware. Now, Sequator, I will show you a link in the description of where you can download this. It's a really good piece of software, probably one of the best out there for just simplicity's sake, and for also just how much you can do with it. And it's a really good piece of software. So it can take in star images. It can allow you to create a new project. It would allow you to create an output file. The output file is a TIFF images, TIFF images, similar to a GIS style image, but it's for in terms of the amount of information is kept in the file for all of the pixel information stacked together. And you can do all different things with the Sequator images. I will show you when we're finished processing how we can load them up and how we can stack them together and do all of the different features on a particular interest. Is the high dynamic range feature, which eliminates a lot of the kind of hot pixels, and also reducing light pollution and enhancing the starlight. And when that is finished, I will be able to show you how that works. So I'll come back to it in a few moments. Okay, so since this is nearly finished, I can show you then the section of the code that it's going to work with now, what the image are going to be processed. So you can see here in this section of the code, the JPEG images are going to be searched in the directory, and all of the individual frames are going to be stacked together. So we can see here the frames. I have a progress bar on the code as well to show you the progress as it stacks all of the images. So it has 46 images, so that's treating it as 46 frames, and they are going to be stacked together. So what happens here is that we have the images, their average, their brightness is divided. They're then scaled with the same width and height of each image. Then each channel is then in the range is then divided and scaled using this section of code here, and then it's all saved as an array, as a numpy array, and it's output as an image in an RGB color scheme. So each of them in the same images, in the same scale, are summed together. Yes, so it's 5,472 pixels are all individually scaled together from each of the 46 images. So again, there's a progress bar for this, and it will take a few seconds, and maybe a minute or two, to be able to go to completion. Okay, so great. After all of that waiting, we finally have our summed image. So let's open it up and have a look at how it turned out. So usually the problem with these images is they can sometimes be over bright, or they can have a kind of a almost like the color or features are kind of washed out of them. And this is annoying, but it can actually be remedied by post-processing the images. And you can see here some of the images that have been processed are kind of too bright. This was taken at a 3 seconds exposure, which is actually to me a bit too much of an exposure, so it may be overexposed. So a remedy for that, and that's what I wanted to get across, was the use of the software Sequator. So Sequator is a really good piece of free software that's very useful for doing exposure images, exposure photography. So let's see. Yes, we can see here that all of our images are output nicely along with our summed image. Our summed image is very important. We spent a lot of time trying to process it, so we have to include it in with the other images. And in fact, this will be our base image. The base image will be our summed image. So our summed image will be our base image. We can load it up first. Actually, let me just go out of here for a second. Let's actually make our project file. So let's output our project. It's in the day 4 one. It's a 3 second exposure. I already made one before doing this video, so I tested it. High dynamic 3 second exposure. Let's call it version 2, or demo version 2, and it will be an uncompressed TIFF file format. So we'll output it here. That's our output. We'll load our base image. Our base image will be, as I said, the DNG only one. We can have it as our one that we output. Our base image can be the summed image, and then put it here so we can see it here. Again, it's completely whitewashed with color, too much color. And here we can say our formats will be then that will load in our other image files are the JPEG ones only, aside from our sum image. But our sum image will in fact be included, so we can actually select them all. And the good thing about this one is that it really isn't that picky. It arranges them in the right format and everything in the right one. So our base image is our summed image, and we can say that we already have the output file. The output project file is the high dynamic range one, and we can actually now begin to use some of the features of Sequator. So Sequator really has a nice high dynamic range, so we can turn it on, and we can also have this feature on, reduce light pollution, enhance starlight. We can have them as the default ones first, and then we can just start. Just take a look at what it has done. Yeah, so now it's output the image of the night area of the night sky that we wanted to examine, and we can see much more clearly than before the individual stars and the areas that are naturally brighter than the background, than the deep sky. This kind of perimeter around the area we're focused on is kind of washed out, but that normally happens with the high exposure photography. So the signal to noise ratio of the center region is much better better than the edges. The edges kind of have this kind of rainbowing kind of effect. So let me just minimize that a little bit. Okay, yeah, and we can actually do some more modification to it. So we had the high dynamic range on, we had reduced light pollution, and we actually have two options for this. We have the deep sky reduction of light pollution and the uneven. So we used the uneven, so let's actually try it with the deep sky one. And with our enhanced starlight, we had it on the kind of strong side, but we can actually increase it even further. And yeah, let's see what that actually does. So we can actually create a new file, a new output file to experiment with this. So let's call it demo version 3 version 3, and that'll create a new file. We can always create new files for any time we modify it. And let's start it again using the same images that we had before, and you can see what it actually will do. And it may enhance the center region and totally negate the external regions, which is actually what we want, because purposefully I flew this, you can see here, in the direction of, so that it would actually be pointing directly on the constellation Andromeda, with the Andromeda Galaxy here, because that was the main deep sky feature that I wanted to take a photo of with this technique. You can also see here the Milky Way, kind of a few nebulas, a few deep sky objects in the band of stars that make up the Milky Way that Cassiopeia, the constellation Cassiopeia, crosses. And this region of the sky is quite nice, again, all depending on the cloud cover, but it was able to get a very clear shot of the night sky. And these are typically constellations you see in the summertime. So it's my hope to do more astrophotography on clear nights in the wintertime, when constellations in the northern hemisphere, such as Orion and so forth, are more visible. Okay, so that's completed its run again, and you can see how it did. So yeah, it's a bit more interesting. The resolution isn't the best, but of course we can actually compare it. We can actually compare it with the other one using images. So let's take a look at the images. It's a 3-second exposure. That was one I did earlier. That was the one I did now. That was the one in comparison. So yeah, you can see the deep sky one eliminates the kind of weird halo effect that we get on the previous one, and this one eliminates the uneven light pollution. So I personally think the uneven light pollution setting is better, so we can actually try that again with the reduced light pollution, uneven, and okay, so that's completed again. We'll take a look at it, and yeah, that's much better. It's even better than before. So you can see here the different features. We have the Milky Way, not the center of the Milky Way, kind of the outskirts, and Cassiopeia, the crown of Cassiopeia, the kind of cone or horn of the Andromeda constellation, and just above the Andromeda constellation we have the Andromeda Galaxy. So if we take a look at it on the images, we have their high dynamic range, version 2, and version 3, and if we go back out of it, that should be our demo of the version 3. So yeah, if we click on that there, yeah, so lovely. Yeah, so that's great. It's really impressive to be able to see some of these features again. They're basically invisible to the naked eye, and even you need a good telescope and a good camera to see them. But to even have the Andromeda Galaxy there, like just sitting there, like in almost full view, is pretty interesting, considering that this is a object that's over 2 million light years away. The light from the Andromeda Galaxy, it's hit the camera, has been traveling through space for over 2 million years, and there it is. And primarily the light is coming from the core of the galaxy, and the kind of region here is the kind of inner kind of spiral structure of the galaxy. And in fact, if we took even more photos, we'd be able to see a much greater disk, because the Andromeda Galaxy is actually quite large. It isn't a small object. It's probably the largest of the true deep sky objects that you can see in the night sky. And yeah, it's pretty interesting to be able to see some of these other stars. Obviously, you see higher density of them here as you get to the band of the Milky Way, and you get to see more structure then of the stars, if they're in nebulas, and or if they're on their own, or if they're part of binary systems and so forth. So yeah, pretty interesting. So that's using the drone for astrophotography. We can start a new project, and this actually illustrates how Sequator works with images that are processed with objects in the foreground when we want to focus on objects in the background, namely the night sky itself. So in these series of images, which I've processed previously using my code in Python, I took images again of the infrared night sky using my drone, but this time I had the drone stationary on the ground to compare it with the images taken when it was in flight. So I didn't take as many images this time, and I had the exposure at 2 seconds, and my reasoning is that the fact that the drone was on the ground, I was expecting it to have better resolution, better focus, but looking at the images even offhand, I found out right away that pretty much the drone was so stable and the flight conditions were so good that in fact the images taken actually when the drone was flying at 300 meters were even better, and the atmospheric conditions were even better. But this gives an interesting illustration of how Sequator works with objects in the foreground, in this case trees. And this was taken at night with basically no ambient light around, but because it was in the infrared, it was able to make out reflectances from the ground and from some cloud, small cloud cover as well. And the trees, even though the image was taken in summer, in July, the trees look red because of the near infrared reflectance. So this proves that it was taken, in fact, in the near infrared. So it should have some interesting features. So let's make a new project in our Sequator of these images. So we can, if we like, we can just upload the star images. They're here in the folder infrared sky. The DNGs labeled as DNGs only, but it actually has the DNG files and the JPEG images, so I can just select the JPEG files here, so there wasn't as many of them as the last time, but it should still provide a good image. So there's about 8 photos here, so you can open and it will automatically select one as the base image. We can designate an output file as the same the same one infrared sky DNGs only. Just say call it output demo, maybe near infrared sky, and maybe call it version 1 as well if you want to make modifications. And this is a TIFF image again, so yeah, so we can put our high dynamic range on, our light pollution effects on with the uneven enhanced starlight. We can just put that on as well for good measure, and then we can begin. Okay, so that's completed, and we can close that and we can see how it has turned out. Yeah, so that's pretty good. We have some areas around the tree here that are kind of reflecting a little bit, but we can make out already some features. So this is Cassiopeia, the W of Cassiopeia. Then we know that it points at this star towards the constellation Andromeda. We can kind of see the cone almost of Andromeda here, and we can see just hiding above the leaf of the tree is the Andromeda Galaxy. Now, there is some differences, of course, namely because of the fact that the tree here is being reflecting near infrared, and it's actually blocking out some of the features of the galaxy. And because this was just a test image, it wasn't focused on the galaxy in particular in this case, but we can do some further enhancements. We can eliminating, because we already know that some of the features have been washed out. We can go merge 4 pixels, and we can also reduce some of the distortion effects. We have 2 options, tele and complex. So I go for the complex option. Remove dynamic noises. We can leave that off. Auto brightness off. Sky region. You can select actually a boundary line for the sky region, and in this case we can do it. So we can say draw our boundary line around the sky area that we're interested in. So we can manually draw it. Boundary line. Well, we can actually say that's an irregular mask actually. Again, it's all experimental. You can pretty much draw around where you want to focus on. Again, it'll get some of the trees in it in this case, but this is the general gist of it. And we'll try to be careful around the Andromeda Galaxy here. We'll try and get the galaxy in, but not the branch of the tree. So we just happen to be lucky. It's kind of circular, so it's in a little circular region. So we can try our best and try to get as much of the sky in as possible that we want to focus on. Okay, so there we have it. So we can then go on to our close that and have a look at it. Yeah, kind of similar to what it was before, but maybe some of the features have been enhanced. We can also maybe change our light pollution setting. Maybe make it as strong as possible. Enhanced starlight as strong as possible. And even try it again. Try that again. Ah yeah, much better. So yeah, you can really make out there You can even kind of make out some of the band outer regions of the Milky Way, the kind of dust kind of clouds and so forth, and in it here, which is very nice. So the W of Cassiopeia, which kind of cuts through one of the galactic arms from our point of view, then points directly to Andromeda, and we see here hidden in the tree the Andromeda Galaxy. So we can zoom in on that with our image that we've saved. So we've saved it in the DNGs only, and we can compare the two images together when we do these different enhancements. So this is the standard stacked image. That was an image, remember, taken from the drone itself, just from the ground. You can kind of already make out a little bit of the smudge of the galaxy here, sitting just above the leaf of the tree. Here it is with the first enhancements we did. We can kind of see the galaxy here, the core of it, and then this is the, let's say, the one that we thought was the best, had the best features. Again, you can kind of see it there. A little bit difficult to make out, but it's definitely the Andromeda Galaxy, and you can kind of make out even the band of the Milky Way of our own galaxy here. And just for a final comparison, Andromeda Galaxy here, and then at roughly 300 meters above sea level, Andromeda Galaxy here. So obviously even flying adds a lot more to the image of the deep sky object of the Andromeda Galaxy. Oops, a little bit too far there. So yeah, you can definitely make it out here that this is the Andromeda Galaxy, and it's much more crisper than the one on the ground, primarily owing to the fact that it's a longer exposure and much more images were taken. Again, 46 images in this image versus the 8 images here, even though this image is still pretty good and actually has some even better features than the previous one. It all depends, of course, on how clear the atmosphere is, your location. I was taking this in a town, my hometown, which is quite near the sea, and it has some kind of high atmospheric cloud cover, but in general these are very clear conditions, very optimal conditions for taking these type of deep sky photography images. And again, the thing to really hit home is this is taken with a drone flying at 300 meters, buffeted by winds, granted not strong winds, but winds nonetheless. The gimbal is still very stable, able to capture a huge amount of photons over exposures that are again 3 seconds long each and made up of 46 images. So 3 seconds multiplied by 46, you can calculate that, how many seconds in total that these images represent in terms of the number of photons captured. So this has been a general experiment into using the drone for astrophotography. I think this is an interesting field, a relatively new field of astrophotography, of using the drone, particularly modified drone cameras, to look at the sky, and not only in mostly near infrared, but also just the fact that you're able to take these sort of images with a flying camera essentially proves that we've really only scratched the surface with the technology that we have at our disposal these days. So this has been a general kind of showcase of how I was able to create these images. Thanks very much for watching. It's a long-winded expose of the techniques that I've been experimenting with, but if you've stuck through it, thanks very much, and please check out the software Sequator, maybe some of my software that I've been developing, kind of Python, kind of toy model codes, and thanks very much for watching. So I'll be doing updates on this hopefully in a few months for when I want to take photography, weather permitting, of course, during the winter time of the winter night sky, particularly of the constellation Orion. So thanks for watching, and see you soon.